Our animals were okay.
Okay, let's go ahead and get started. So we did not have class on Tuesday because of the no snow day. So we're going to try to play catch up a little bit. I looked over all of your quizzes, and if you gave yourself a grade, I went with that grade, and if not, I've marked some things for you. I wrote some feedback on some of them, but for the most part, everybody was doing really well. All the responses were really nice. A lot of people like that snake example. That's just one of my main takeaways. But I'll upload your quizzes with my annotations to Canvas after class today. And I'm not sure how long that'll take me because I haven't done that before. And Canvas is super fun about that. Okay. So if you remember our last class, we had a question about this visual illusion. So here's the name of this, and to give you a little bit more info, it's the question was kind of like at what level of perception or processing are these edges formed that aren't really there. And so you can look this up. There's Wikipedia on it. There's a few papers on it. But the concept is this illusory contouring concept. So there's some others like this. But to kind of give you the answer, it's thought that those edges that aren't really there are created in early processing in visual cortex, so V1, V2 area, which are two networks that kind of feed back to each other. And that's where they believe those edges come in. So that's pretty early in the process, not really pulling on any experience or memory or anything like that. So I just thought that was interesting and I thought I'd share that. So previously we talked about cognition. So just to give you a little bit of a refresher on what we talked about last time, we talked about cognitive psychology in general, methods in cognitive psychology. Basically, the idea was that cognitive psychologists like to create models, test those models, refine those models, and those models should be able to explain what goes on in the world and also predict what's going to happen. And they have to be testable, and so you test them, you refine them, and you want the simplest model possible. So some of the approaches used in cognitive psychology that we talked about briefly, behavioral observation, usually in a lab, looking at patients who have certain areas of their brain damaged and how they function on task compared to patients who don't have those areas of the brain damaged. Cognitive neuroscience is now a field which looks more at brain imaging, and we talked about different methods of brain imaging. I did not fix my typo about fMRIs, so I feel bad about that. But we also talked about working memory and long-term memory being the two kind of main ideas in terms of cognition. Working memory being this place that can maintain a limited amount of information for a short amount of time. Like if I gave you a random string of numbers, you could remember that as long as you kind of rehearsed it in your working memory. It'll take you some practice to commit that to long-term memory. And so we talked about different models of working memory. This is kind of one of the standard ones that represents a lot of the others, and this idea that you have kind of these buffers. There's one for audio, one for what you're seeing, and then a connection back to long-term memory for like your experiences and kind of your expectations about a domain. And then all of that is being orchestrated by what's considered a central executive process. Some of the studies that we looked at the performance of working memory, and we saw that in general, as time goes on, memory recall gets worse. We also looked at primacy and recency. So if you give somebody a list of things to remember, they'll probably remember the first things and the last things and not so much what's in the middle. And so that's pretty much everything I just said about working memory. Main thing for HCI is we want to keep working memory as free as possible. So people, it's a limited resource that the human has, and they need to be using it for the task they're trying to complete, not trying to understand our interface or having to do things that our interface could do for them. And so the example of that was showing instructions throughout the process instead of just giving them all at once and then expecting the user to remember that. Long-term memory, we talked about briefly, different categories of it. For HCI, the main thing to remember is that we don't depend on long-term memory. So this, for people who are experts at certain systems who use them in a professional way, like if someone is a 3D animator or a video editor or something, you're going to see them, if that's their job and they do it all the time, they're going to use keyboard shortcuts, they're going to do things that it's all procedural memory that they have, and that's long-term based. But when we create an interface for a large group of people to use, we don't want it to be something they have to be trained on in most cases. So that brings us to today. We will talk about more cognition, and we'll talk about Don Norman, who is a pretty influential figure in human-computer interaction. And we'll start to talk about design guidelines and some of his design guidelines. And then as we go on Tuesday, we'll bring in more guidelines from different people, different subfields within HCI. And that'll get us on our way to building prototypes and actual interfaces. So we left off with dual process theory when we were talking about cognition. And so dual process theory has many names, and it goes as far back as this guy, William James. He's from the late 1800s. He's kind of one of the fathers of psychology. And so even he kind of recognized that human cognition, the way humans operate, we can think of it roughly as two systems. One that is very responsive, very fast, almost not something that we're consciously aware of. It just processes things and responds. And another that is more deliberate. And he called the second system the true reasoning system, and the faster system the associative reasoning system. From that point onward, many psychologists, social psychologists, cognitive psychologists, even some sociologists have run with this idea and made models that are based on dual processing. It's something that kind of explains a lot of the biases that we observe people have, things like stereotypes. A lot of the mistakes that people make in certain situations can be traced back to kind of a dual process theory. There's been a lot of evaluation of this idea, whether that's through neuroscience or cognitive psychology. And I guess the most legitimate and probably, profound criticism of this idea is that two systems are not enough to describe what's going on. And it's pretty well accepted that obviously human cognition is really complicated. There are a lot of subsystems. And so this doesn't necessarily conflict with the idea of these two systems, but some people believe that for example, that 4 subsystems are necessary instead of just 2. We'll stick with 2. That's pretty much the mainstream belief. but once we talk about the two, feel free to look this up, and you can read about the models that have 4 subsystems. So this is the cover of a book called Thinking Fast and Slow. It's by Daniel Kahneman. He's a psychologist and an economist. It's a really popular book. I think it came out like in 2012 or something. It's a really good book, a really interesting book. He's done a lifetime of research working on things like cognitive biases, and we'll look at a number of examples from his work. And so this is kind of, probably still today, represents a pretty good summary of where we stand on all the research that we've done and about these systems. Let's see, yeah, 2011 is when that book was published. So, dual processing theory, we have what we call System 1 and System 2. They've had other names, and in other models they might be called implicit or explicit, things like that. But for the most part, we'll call them System 1 and System 2. System 1 is considered to be implicit. It's fast, unconscious, automatic, parallel, not really subject to the limits of working memory so much. System 2 is a more explicit process. It's very slow, very controlled, one thing at a time happening. And then a little bit of criticism is that maybe this is more of a continuum than these two distinct areas, which of course is probably always a little bit true. So let me give you some examples, some more attributes of System 1. So this is kind of an automatic system, really low in terms of like the effort that you have to put into it. This is the kind of thing that you may not realize is affecting what you're doing, but it is. This is something where we use context and domain and past experiences. So when we go to meet someone, typically in the South in the US, you might shake someone's hand when you meet them, that kind of thing. And you would know the context where that would be appropriate. So like maybe that would be you're meeting someone who's, you're at a business meeting or something, someone that you're going to work for, versus meeting, a classmate or something in class where you might not do that. So things like that are System 1 processes. System 1 processes are also things like, getting out of the way if something is coming towards you. These are things that can be really simple, like handing something to someone, for example. That's a really complicated thing to hand off something to someone. And you might not realize it until you try to get a robot to do it. And it's complicated, but it doesn't tax us to do it. It's just there. It's a procedure, and it goes. So this is also tied to what we would consider the evolutionarily old part of the brain, the reptilian part of the brain, kind of very stimulus response. Also tied to emotions, though emotions are certainly a two-way street. Depending on what happens first, the cognition or the emotion, they can go either way. So we'll see some more examples of this. System 2, though, is exactly the opposite of System 1. So it's more about conscious reasoning. This is like doing a math problem. This is something it takes a lot of effort. It's a generic process. So it's kind of like, problem solving, just general problem solving. When you encounter something new and you don't know what to do with it, and you stop and you have to think about it and take it a step at a time. This is obviously something that's going to be limited by your working memory, and it's very serial and sequential. You can't do the two of these things at the same time, and it's because it is in working memory. So this is pretty much any kind of conscious reasoning. So there's also what's called a cognitive steering process, which is kind of the connection between these two systems. So obviously, System 1 has to have a way to queue up system 2 to say I don't know how to automatically handle this, and more effort needs to go into it. And so that's also something that you can do. So we see studies about people who have stereotypes, and everybody has stereotypes because it's very helpful for us to be able to live and communicate and be social. We have certain things we expect of people, and a lot of those are tied to race or gender or religion or wherever we're at. And so people can actually suppress a lot of their kind of system 1 reactions if they think about it consciously, but it occupies the system 2 slot to do that. So kind of the fun part about the system 1, system 2 thing is to look at some of these cognitive biases that exist. And so that book that I mentioned, Thinking Fast and Slow, obviously fast and slow are the 2 systems. A lot of that research is all about biases. And so it's really interesting. We'll talk about a few of them. So one that's pretty strong is belief bias. And so what that is basically, it's exactly what it sounds like. You use your prior beliefs to influence how you assess a situation. And so it's a top-down process, and rather than thinking, like stopping and thinking like, oh, maybe I should just look at the facts of this scenario and not use my previous knowledge, this is part of that system 1 process that because you've observed things, you have an idea of how things work, you have certain beliefs, this will take place. And I'll show you some examples of that in a minute. Representativeness heuristics. This is really interesting. So these are the 2 fallacies here that people are pretty much always susceptible to. The first is a small sample fallacy. So we tend to think that even if we have just a handful of people, as long as we feel like they represent the group, like the bigger group that we're thinking of, we'll assume that whatever is said, whatever that comes out with that small sample applies to the whole group, and this is rarely the case. Base rate fallacies, we'll see an example of this. It's basically we often fail to take into account just general facts about the world, like how many babies are born in the Starkville Hospital, in an average week. Most of us probably don't know that information. But if we set up a scenario in a certain way, we would assume, a certain number or something, and work off of that base rate fallacy. Availability heuristics are another big one. So basically, we judge how frequent something is based on our own personal experiences, or specifically if we've heard about something recently, we will misjudge the frequency of it happening. So this is one of the studies done by Daniel Kahneman, who wrote that book. This is the conjunction fallacy. And so in this study, what they did was they had people read this paragraph. And it says, Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice. She also participated in anti-nuclear demonstrations. So then you get these options, and you're going to rank the probability of these being accurate descriptors of Linda. So we've got some things about her profession. We've got things about her being active in the feminist movement. And then we've got some of these combinations of a profession plus active in this movement. So we asked 3 groups of people about this, and so we had the naive, the knowledgeable, and the sophisticated. And so these were undergraduates, graduate students who had completed so many stats courses, and then PhD students who were getting their PhD in decision sciences, I think is what they called it, but it had done a lot of coursework about this. And so this is the likelihood that people thought that Linda was a bank teller in white. So and lower is a higher likelihood. So what we see is that blue is the likelihood of her being a bank teller and a feminist. And so we see across all groups, people thought it was more likely that she was both a bank teller and a feminist than just a bank teller. It's not possible. So there's a conjunction rule for probabilities, and basically the probability of a joined statement like this is never more probable than just the single part of the conjunction. But because of biases at play in our experiences and the description of Linda, this is the kind of result we get. And we see it's the same across all of these groups, even people who should know specifically about this kind of thing. So, and that one, that's the conjunction fallacy. So here is another one. It's kind of interesting. This is a framing effect. And so this is two different ways we're going to frame the same scenario. In this first one, we're imagining that we go to see a concert. We paid $20 for our ticket. We're about to go into the concert. We realize we've lost our ticket, but we could buy another one for $20. And we have currently $60 in our wallet. Okay. And so the question is just, would you buy another ticket for $20? The second way of presenting this is that we buy a ticket that costs $20. We get to the concert. We realize that a $20 bill is missing from our wallet. And we still have $40 left in our wallet. We're going to buy the ticket. We don't have the ticket yet. But we have $40. Will we spend the $20 to get the ticket? So these are the same, you're going to have the same amount of money when you get done with these. If you buy the replacement ticket or if you just buy the original ticket and you've lost your $20. But what we see is that in this first one, results 46% would buy another ticket. In the second one, 88% would buy a ticket. And this is because we group this background information that we've already bought a ticket and that we've lost it as part of the financial outcome here. Even though in both cases we would see the concert and have the same amount of money, it's more likely in this first case that we won't buy another ticket. Now another example of the framing effect is in the way that we word this question. And so they asked people, either solve problem 1 or problem 2. And so you imagine that a country in Europe is preparing for an outbreak of an unusual disease. It's expected to kill 600 people. We've got to choose from 2 programs. So program A, if we take that, 200 people will be saved. Program B, there's a 1/3 probability that 600 people will be saved, and a 2/3 probability that 0 people will be saved. Which program do you choose? So in this case, we're using language like saved and trying to, we're framing it in terms of keeping people alive, basically. If we look at problem 2, so it's the same situation. Program C, 400 people will die, okay, for sure. Program D, there's a 1/3 probability that no one will die, and a 2/3 probability that 600 people will die. So all of the people will die in that case. But we're framing it now in terms of people that die, not people that live. So what we see on the first one, 72% choose program A, saving the 200 people. In the second one, we see that 78% choose program D, where there's a 1/3 probability that no one will die. 2/3. It's more likely that everyone will die. And what this is being risk averse in problem 1. So we see this certainty of saving 200 people versus in problem 2, when we look at this, we're optimistic about kind of saving all of the people. The expected outcomes for all of these are the same. So you can see where these cognitive biases can matter quite a bit when making decisions. This is another one that's more classic, and this is about just financial outcomes. And this is also a common problem. But basically it's about being risk averse or risk seeking. I won't go through all of this, but you can look at it if you'd like later. And it's fairly interesting because the overall point is that people don't compute expected values naturally when they look at a situation. They let these biases kind of drive their decisions. So what does this mean for us, designing interfaces, designing machines for people to use? So kind of the best guidelines that we can come up with, first of all, we want to provide all of the options in an unbiased way, typically. And we want to help people find the alternative paths that they can use. If we're visualizing data, unbiased visualizations are very important. And we'll talk in a later class about visualizations specifically and how they can be deceptive or misleading. Other things we don't want to do, we don't want people to have to do things that computers do well. Calculating things, remembering things, all of that should be in the system. And basic assertions and assumptions, the system needs to take care of that. So these are steps to kind of guard against these biases. So we can think of it as if we're doing decision support, we're helping system 2 override the responsive system 1 process. Data visualization, and when we talk about Don Norman stuff, we'll hit on this a little bit. We're going to try to use system 1 to support system 2. So when we look at something visual, that system 1 process interprets that. And that's why if you have a biased visualization, it can really kind of throw off decision making because that's system 1 that's interpreting that. And then this is an area we'll look at towards the end of the semester. Basically using tricks to get around system 2, to keep people engaged in our system or trapped in our system or using our app or that kind of thing. So persuasive computing is a whole area, and we'll talk a lot about it. But these are things that are used when you're making like games or social networks or things where you're really trying, your goal is to keep your user engaged with your platform. And so that's a huge area of interest, especially for kids and developing, and people are worried now about screen time and what they're doing and that kind of thing. And so that's evolving pretty rapidly. But a lot of the techniques that are used to keep people engaged with applications or devices are centered around these biases. Okay, so that sums up a lot of the cognition stuff that we'll talk about. Now we're going to shift more into looking at things that can be directly applied to designing interfaces, designing products, machines. So we're going to start with some design insights from Don Norman. So Don Norman has, he's a researcher in the field of HCI. He's written a number of books. The first book he wrote is called The Psychology of Everyday Things. He published that, I think, in 1988. And so then he went on and wrote things that make us smart. And then in, I think, 2002, he published this book, The Design of Everyday Things, which is just this book, really, with some changes. And this book is a huge success. Has anybody heard of this book? Read this book? Okay. So this is kind of one of those foundational books that you probably should read if you're really interested in this field. I didn't assign it as reading or anything because it's kind of time-consuming to test over that and everything. And I think if you are interested in the things that we talk about from it, I'm going to try to do highlights from it. You should take some time to read it. It's not a long book, and it's really interesting. So he read a few more books. I don't really recommend these. I've read all of these books, but he just kind of whines a lot about the same thing. When I took my undergrad HCI, we had to read all of them. And so reading them all back to back, I do not recommend. So anyways, in 2012 or 2011, we did the third version of the design of everyday things. And so it's pretty popular. I've been rereading it because I hadn't read this version, I've read the previous version. And it's very good. It's up to date on a lot of things. So let's talk about kind of what we would learn about from a Don Norman book. So the big observation that the design of everyday things looks at is this idea of affordances. And this is a concept from a guy, Gibson, who's a psychologist. And his focus was on looking at how objects in the world kind of inform us about what is possible with those objects when we interact with them. So we can say simple things like, a button affords pressing. We look at it, we can see that it's something we can press. A table can afford a lot of things. It can afford setting things on it. It can afford the fact that you can lift it up. Pretty much whatever you naturally gather from looking at an object in its environment. And it's all about the relationship between the person and the properties of the object and what the person perceives as possible with the object. And so the idea here in terms of HCI was that when you build a thing or an interface, you want to capitalize on these affordances as much as possible. That's what makes something intuitive to use when you've never used it before. If you can look at it and intuitively have an idea of what it can do, this is a good thing. This is reducing the cognitive load that it takes. It's reducing any training or learning. But this got a little out of hand. So people started to say, oh, I put 3 lines in the top corner of the mobile interface. That's an affordance that there is a menu there. That's not true. So in this latest version of this book, it's kind of addressed signifiers. Signifiers are something that communicate about affordances. So the little 3 lines signify that there's a menu over there. Things like text written, like with instructions next to something, those are signifiers. A lot of things in interfaces that are designed are just signifiers. They're not necessarily affordances. So if you, in your interface, put like a different texture on something that's meant to be, a place that you touch or something, well, the device itself is what affords touching. The thing that you've put is a signifier to show where to touch it. And both of these things are needed in terms of designing an interface or a product. So in Design of Everyday Things and in all of Don Norman's books, he has a lot of interesting examples just of things that he sees kind of in everyday life. They're not all technology related. So I've pulled some of the more interesting ones for us to look at. Doors are a big thing for Don Norman. And we've all encountered confusing doors. So in some cases, if you have just like a pure glass door with no clear indicator of, which side of it is hinged and which side is the push or the pull, that's very confusing. There's no affordance there. And so you can see, like, obviously, here are your signifiers, right? Your instructions, basically. And the original, I guess, claim kind of that Don Norman really pushed was that, it's bad design if you have to have these signifiers. And that's certainly true. It's better if you don't have to have the signifiers. But he's kind of backed off on that position, especially since we've gone to things that are more, everything's just on a touch screen and the affordances are limited. So that's kind of the big thing with affordances. This one is interesting. So this is an accidental affordance becoming a strong signifier. And so you've got this ledge here on these stairs, which does afford setting something on the ledge, right? And then actually as someone sets something, that kind of becomes a signifier that, hey, other people, you can set things here too, which leads to this kind of thing. So these things are dynamic. They're not necessarily set in stone. So once somebody begins to use something, the affordances may lead to other affordances or signifiers being developed. So the next thing that's a big part of kind of just looking at the design of everyday things is conceptual models. And so this is an example. This is a refrigerator freezer, and you've got these knobs to adjust the temperature. So everybody encountered something like this. Okay, so you've got, like the top section is a freezer, the bottom is a refrigerator, and you're going to use these knobs to change the temperature in the two areas. So how would you think this would work, just intuitively? Independent, yeah. Right? So if I want to change, my freezer temperature, I should just be able to turn this knob, and it just changes the freezer, and this stays independent. Turns out in most cases, and still today, this is not how this actually works. So this is the system that we imagine, right? Here is our little control unit for our refrigerator. We imagine there's a temperature sensor in here, and that there's some cold air being pumped in here, and we're controlling that relationship. Same thing for the freezer. This is actually how most of these units work. So in this case, you have a single temperature sensor. It's in the freezer. You have a single cooling unit, and there's a valve. And so the cold air is going to both the freezer and the refrigerator. The refrigerator control is changing the valve, while the freezer control is adjusting this temperature matching that's going on. It's a very non-intuitive way of looking at this. And kind of the bad part about this is that it takes time once you turn this knob for anything to happen. And so even if you were to conduct a scientific study on your refrigerator here and measure the temperature once you change a knob, it's going to take you a while to come up with this model. And so the main message here is that the user's at a huge disadvantage. They're going to be really unhappy and confused because this is not an intuitive model to most users. This is not what you expected at all. And so this is something to think about when we're designing software and systems. The user's concept of how the system works is very important. It doesn't necessarily have to be the case that their concept is how it actually works, but it has to be close enough that it doesn't matter. It's certainly best if the user's concept is how it actually works. So the next thing that we can gain from Don Norman's work is this idea of a gulf of execution and evaluation. And this is kind of a way that he breaks down how people interact with a device or a system. And basically, they're going to start with a goal, and that's going to lead to this goal of execution, where they're kind of exploring the system, trying to figure out how do they use it, what can it do, and then it's going to make a change in the world, and they're going to look at that change and evaluate, does this match up with my goal? Is this what I wanted? And so we can elaborate on that a little bit more. So he's got this 7-stage model of how this is working. And so this is where you come from your goal, when you execute, you plan, specify, and perform the action. Then you look at the world, perceive what's happened, interpret that, and compare that to the state you were hoping to reach. And so he's also, I didn't include this in our presentation. So he's got these 3 levels of processing, this visceral, behavioral, and reflective level. And the main thing from this is it's basically an argument that things should look good at a visceral level. When you look at an interface, it needs to look nice. That's a big part of it being usable. Even though you could build an interface that doesn't necessarily subjectively look nice, but is very functional, it's not going to be rated as highly or as pleasant to use as one that looks nice. And so this is these same things, but at these different levels. And so basically this visceral level is very low level. This is about, in the case of output, like actual actions that you're taking, like clicking a button or turning a knob, and in terms of perception, seeing the change that made. And then you move to a behavioral level that's saying, I want it to do this thing, did it do this thing, interpreting what's actually happened. And then when you're at this planning or comparative level, that's a much higher level, abstract kind of thinking process that's definitely like in the system 2 side, and could even be something that's a long-term goal. So thinking about this from kind of the perspective of the designer, these are questions that you can ask to basically answer the user's questions. So these are just those phases. This feed-forward and feedback idea. What do they want to accomplish? These are some of the same questions. What can I do? How do I do it? What does it mean? What happened? The main thing to take from this 7-stage kind of model, and we'll see other people's models that are similar to this, is that you want to think through that experience that someone who's never used a system is going to have. And you don't want to, you want this to be a pretty tight loop. And we'll talk about feedback and errors, but this needs to happen quickly. With the refrigerator freezer, this doesn't happen very quick, and it's frustrating. If people are able to explore a system and try things without any negative consequences to that, and even better if the system gives them helpful feedback, that's something that will be very useful and people will like that system a lot. Let's see if there's anything else. So, okay, let's talk a little bit about natural mappings. So the example that's kind of, I guess, the giant, oh hey, I left, that's not supposed to be there. But think about a stove. Everybody's seen a stove to cook on. Yes, okay. So in a lot of cases, there are 4 cooking surfaces that get hot when you turn them on. And the big question is often, you've got these knobs to turn them on to a different temperature. Where do you put the knobs for each of these surfaces? And here are some options. So a lot of times we'll see, okay, so I should say, the easiest way to do this would be to put the control for each burner like on the burner. But you can't do that because it will get very hot and people will burn their hands when they try to turn them off. So we get stuck with this idea of they're going to have to be off to the side somewhere. And so sometimes we'll see stoves with them labeled. Often you'll see them with little pictures of the stove, maybe showing the 4 burners with the burner that it activates being highlighted. But essentially, there's not a great answer for something like this. There's not an entirely natural mapping here. You could certainly put 2 down here, 2 over here, but that's not really helpful either. So most of the time you'll see some kind of legend that tells you what controls what. On the other hand, this is like a power seat in a vehicle. And these are little slider controls that move the seat forward and backward, up and down, tilt it back and forth. It's essentially a tiny version of the seat down there, and you're just kind of moving it. That's really natural. It's really straightforward. The only thing that could be more straightforward is if you directly just moved the seat. But that kind of takes away the benefit of the power seats. So this is kind of the mapping that is the closest you can get to the natural mapping. But the idea to remember here is that the things that control something should be close to the thing they control. Okay, so let's talk a little bit about design constraints. Don Norman talks about 4 different kinds: physical, cultural, semantic, and logical. So we'll just talk about the physical ones with this example. So the example he's giving is putting batteries into something. And so if you put batteries in something, there's a positive side and a negative side, so like a AA battery. And you have to put it in a certain orientation for it to work in most devices. This is something that we will often do wrong and then just swap them until we get it to work. It's a little more frustrating whenever there's a bunch of batteries. But what is pointed out here is that this really didn't have to be this way. We could have designed a battery in a way that it didn't need to be put in a certain orientation. So imagine if instead of this side being positive and this side being negative, each side had a positive ring and a negative ring. And so we see things like this, like in our connectors for your MacBook or whatever. These are symmetrical. It does not matter which way I rotate this. It's the same thing. We see it in USB-C connectors now. Upside down, there's no orientation. We don't see it in batteries, and we won't see it in batteries. And this is kind of one of those things where you could change this, but you won't, because there's so much equipment that depends on what we already have. And so there are some other things you can do to try to mitigate this with specific devices. Microsoft actually has a patent on a way of using just regular batteries, but it not mattering which orientation you put them in. Obviously, it adds expense to building the product, and so no one does it. But this is just something to remember when you're early on in a design. It can really matter down the line. Just to mention, I don't have any figures or examples on the cultural or semantic and logical constraints, but you want, in terms of culture, you want to be aware of what things mean in the domain you're working in the place that you're working in, and how you can leverage those to constrain something. So constraints can be used to prevent errors as well. In terms of semantic meaning, so things like, you think about like a car as brake lights, right? That has a meaning to people who drive. That that car's about is stopping. When we have autonomous vehicles, will we need brake lights? Maybe, maybe not. If all of the vehicles are autonomous, what's the point really? And then logical constraints. So a good example of this is if you were to, like, say you're going to repair a kitchen sink faucet or something. You take it apart, you repair it, you put it all back together, and then you've got like this extra thing. Okay, that extra thing is a logical thing that's telling you you did something wrong. It's not repaired. It's not back together. Although I have had my share of extra screws at the end of things, and everything's fine. So talking a little bit about applying affordances and signifiers to everyday objects. I just thought this was interesting. Don Norman is really upset about this light switch panel here because he didn't know what the lights went to. And so in his home, he says, his light switch is like this little floor plan of his house with the switches on it, which certainly, it puts the control right where the thing is. I don't know. It seems a little crazy.
Doesn't afford you very much malleability if you change the light orientation, if you change the fixture.
Right, yeah. And I guess, I'm not sure if he had this in the old book or not, but like certainly now, smart home kind of thing, right? This could all be software, and that's, easy enough, but this is a physical thing, so yeah, if you change anything, you're going to have to update that. Okay, let's jump to errors. So we can think of errors as two categories, slips and mistakes. And then within those two areas, we can kind of divide them further. So if we're looking at slips, it's basically you're trying to do the right thing, your goal is good, but somewhere, some action you take is not correct. So this can simply be forgetting something, right? This happens, especially if it's a task that requires your attention and you get, somebody says something to you and you look off and you start doing something else, and then you come back and you're not necessarily back in the right context. So if we look at mistakes, those can be in these three categories. We have rule-based, knowledge-based, and then just memory lapses. So memory lapses can comprise either side of this, but mistakes are more thought of as the goal or the planning being incorrect. So like this could definitely be a knowledge deficit. If you're not completely informed about what you're doing, you can make a mistake because you're using knowledge that's not the knowledge that you need to be using. And this does leave out the idea of malicious intent, so we'll just kind of ignore that for now. So back to that model that we looked at earlier. So dividing that into the slips usually happen in this phase of things where we're performing or perceiving actions, and these are very subject to working memory constraints in this area. And then whereas mistakes happen at this higher level of goal planning and abstract thinking. So, some design principles for dealing with errors. You want to provide kind of sanity or sensibility checks when you can. And you may not always be able to, because in a lot of cases, the whole reason there's a human using this interface at all is because there's something that we can't automate. But you do want to validate things. You want to always be able to undo things if possible. So users will feel a lot better and be willing to explore and learn a system or a product more if they feel like they're not going to make a critical mistake that's going to break everything. So it's really important to make it evident how to undo something. And it's even of higher importance that when a destructive action is going to happen, that's not going to be something you can undo, you really need to get the user's attention. And so this is an example of kind of what's called a lock-in function, and this is just like you try to close a document that you've made changes to and you haven't saved them. Today, a lot of software will just automatically save that for you and won't bother you with this. But in some cases, we don't do that, and so we still care about something like this. And these are things that need to get the user's attention. So sometimes if it's more critical things, like if you've ever used some cloud hosting providers and stuff where you're creating like infrastructure and things, and you want to like destroy a bunch of virtual machines, it will make you type in some specific phrase to really ensure that you're paying attention, that you're destroying all of this stuff with one click. But in general, we want to promote discovery being easy and correction being easy whenever you do make a mistake. And we don't really want to treat things that are wrong as errors in the sense of we don't want to be mean to a user about it. You want the system to be helpful. For the most part, people don't like interfaces or systems that are mean to them, that are very assertive. That's not always true, but for the most part, that's a good way to go. Okay, so the last thing we'll talk about today is the paradox of automation. And we'll talk a lot more about this when we kind of do a class on just bad HCI and things that have gone wrong. But the idea is that we often automate things that are dull, dirty, or dangerous. So things that are boring for humans, things that humans have put themselves in substantial risk if they were to do them, or things that humans just don't enjoy. And so when we create a system that's automated, that can do things on its own, it's usually pretty good about this, but occasionally a system that's automated will not know what to do with a certain thing that it encounters. So kind of the longest running example of this is aviation, commercial aviation. Autopilots, all of the systems on a plane, there are a lot of them that do things automatically, that make flying the plane possible and manageable. The main problem is that 99% of the time when you're flying the plane, everything works as it should. And that's what you get used to if you're a pilot and you fly. The 1% of the time, and don't quote me on that 99%, I don't know what the actual percentage is, but the rare time when something fails, first of all, you're not expecting it. So you're not really necessarily in the system, you're not in tune with what all of these systems are doing, okay? So when it fails, those systems disengage. They're done because they don't want to be responsible for making, things worse. So oftentimes automation fails, it immediately just sounds an alarm, hands it over to a human. Well, now the human has to, first of all, get into that context to figure out what's going on. They were doing something else, most likely. So now they've got to try to understand the state of the world this system's in. And then they've got to somehow repair it. So whenever this happens, we refer to humans as being out of the loop. This is also the case, sometimes you'll have factories, manufacturing facilities that are considered dark facilities in that they're completely automated. Basically, you have people bringing in the raw material and picking up the final product, but inside the factory it is literally dark, the machines do their job, and they move on. This is really nice. It doesn't cost a lot of money to run these because you don't have to have people there all the time. But oftentimes, when these things fail, it is more expensive than if you ran a system where you had people there all the time. Because getting people there quickly enough to understand what's going on and what needs to be fixed is complicated. And So in the case of factories, it can be something that seems pretty straightforward, the process, but the number of systems that are tied together and how they are designed to reflect their own state, it's really difficult once you're out of the picture, out of the loop, to get back in there and to fix it. So this leads to a lot of bad outcomes. Pretty much, I would say a majority of modern aviation accidents are a result of automation handing over to humans and humans having a misconception about something specific that's going on. Or in some cases, it's not even that the automation has failed, but that the human is unknowingly fighting automation. Automation is trying to fix something for them in the background. They don't realize that's happening, and they're actively working against each other. So some headlines that are kind of relevant today as we start to look at vehicles that have assistive features or vehicles that are fully autonomous in driving. What do they do when they encounter a situation that they don't understand? In most cases, they just quit. And that's fine. I mean, that's kind of the default that we arrive at, even just for legal reasons, right? We have a strong idea about responsibility and humans being responsible for bad things that happen. We want to be able to point back to a person. And we certainly don't want automation to be responsible for these bad outcomes. But it's a real question in terms of once a human is out of the loop, can they actually get back in quick enough to help something? So in aviation, when you're flying a plane, you actually have quite a bit of time in most cases to get back into context compared to something like driving an autonomous vehicle on the ground. It's not nearly enough time, I'm sure, for the people doing it. But when you see these accidents that take place, you will see a lot of deliberation, a lot of processing going on, several minutes worth, from the time the automation fails to the time that the whole scenario is over. Whereas when we're looking at things where we're handing off quickly, like an autonomous vehicle, in this case, I guess like a year ago or so, we had this Uber self-driving vehicle that killed a pedestrian. Okay. So the safety driver was in the vehicle. The safety driver was watching, say Hulu, yeah, Hulu, on their phone because the car usually does a really great job. It's a good system. It drives. The safety driver doesn't want to just sit there and look at it. But as soon as it needed the safety driver didn't have time to get back in and to stop it. There are a lot of other issues with this Uber thing, but for our purposes, the idea is that they were out of the loop, and it was really difficult for them to get back in the loop. We won't be building systems that are quite this intense in their outcomes with people being out of the loop. But one principle of design that you're going to want to keep with you is that you want your system to be very clear about what it's doing and what the user needs to do. And so you want to keep the user engaged. What's interesting is, like, we're talking about the factories that are kind of dark or whatever. They will actually pay people to operate those factories and do nothing. And they actually create fake tasks for them, where they have to push a button, every so many seconds, or attend to a stimulus, because otherwise they're just going to stream Hulu and then crash into someone. And so that's something to think about in specific domains like that. But for us, it should always be really clear what the system is doing. But we shouldn't err on the side of being too verbose. You don't want it to be annoying. So there's a balance there. But it's important to be very clear and to be collaborative with the user. So if the user is engaged with your system, with your interface, you're not going to have this handoff problem as much. And for us, these handoffs would probably mean, someone losing data or not submitting something that was important and not realizing that they didn't do it. And so that's what we want to avoid. That's everything I have on Cognition and Don Norman. So when we meet on Tuesday, we will do a quiz on Cognition. And then we'll move towards more interaction design concepts. We'll look at prototyping things. We'll look at more general user interface guidelines, that kind of thing. I'll post your quizzes that you took last week onto Canvas. And then I guess I'll see you guys on Tuesday.